So how to generate images using ultrasound. So let me first show you a basic ultrasound is you can think of, you send a wave which through the tissue, and tissue is composed of different types of organs, especially interfaces, and their property of the sound wave with respect to interaction of sound wave are different from each of these, so that when wave propagates, if they meet an interface with different property, some part of the wave will reflect back while some part will transmit. Well, we are interested in the waves which is reflected back from the interface. And because in ultrasound, we know roughly the speed of the sound. So when it reflects back, we just measure the time difference, which we call as a time of flight. And then we can back calculate where were the interface location. And this is a pretty simple, and luckily the sound waves are propagating slow enough that we can use our electronics to detect this time difference very accurately. So that's how we generate the ultrasound. So let me give you an example, typical example of fetal imaging with ultrasound. You see, this is when someone has a baby, then this is the first image of the baby by using ultrasonic imaging. You can see the sound waves coming top to bottom and hit this interface and measure it so that we can reconstruct these images. And then how can we generate these sound waves, a pulse of sound waves? And there are various ways, but one typical one is a piezoelectric crystals. As I told you before, piezo is a pressure generate electricity. On the other hand, you give electricity or voltage changes that will generate a different movement of the PGT surface that will generate pressure wave, which is ultrasound frequency right now. So we can also focus ultrasonic imaging by using a concave shape, because these, by making this vibration, we can create that wavefront as a focusing. And also the resonant frequency of this ultrasound is in megahertz range. So when you visit a clinic, you may take a look various different kind of ultrasonic transducers, and you may be able to find their frequency range, usually megahertz. So 1 to 18 megahertz. The range is safe with tissue and not audible to human, because our audible range is about 20 to 20 kilohertz, not this megahertz range. And also important thing you understand is this is a frequency that higher frequency is usually giving higher energy, while that higher energy gives you a better resolution. Our tissue, and in general, tissue responds to higher frequency with a lower penetration. So there's always trade-off. You use higher frequency ultrasonic transducer, you gain a better resolution. However, you may not be able to penetrate deep enough. So for example, if I want to use ultrasound to image my whole gut or like heart, you may have to use a lower frequency. While if you use like 10 megahertz, you may not go very deep inside while you have a better spatial resolution. So how do we detect structure? So basically, it's the same as when we are in the mountain, we say, Yahoo, and that the mountain in front of us will have our sound wave reflected back, and we hear the echo. And based on the time of this echo, we kind of calculate the distance of the mountain in front of us, whether it's closer or far. The principle is exactly the same. The only thing is we are not using sound wave inside the air. We are using ultrasound inside aqueous medium, inside the body. So echo of sound waves that bounces off at tissue interfaces, we just use this one for detect the structure. And that echo or wave reflection, which return back to the transducer, we measure them, the travel, yes, time by using PZT crystal in reverse. So this is quite interesting that, so we use piezo for generating sound, okay? Generating sound, and that sound goes and then hit the interface, and then it reflects back. And during time, when we generate sound, we give a voltage input to piezo to generate this pressure wave, while the reflected pressure now returns back to this transducer, and that PZT having this pressure or generate a tiny of voltage difference, and that we sense. So using this as a both actuator and sensor together. So that's why I put it in reverse. If we split the time, then we can use the same piezo crystal for generating ultrasound and detecting the reflected ultrasound. And the B is when we have this 2D structure, if we move this 2D on the side by side and reconcile, we can create even this 3D shape of ultrasound. So now let's get into a little more into this. And so the spatial location of each echo can be determined by the, yes, time of flight. That's the time between the generation of the pulse and then reception of the echo. So let's understand about the speed of ultrasound or speed of sound is assumed usually in tissue as about 1.5 kilometer per second. Remember, our sound wave propagates in air about 330 meters per second. And in fact, if it's in water, it's like almost 5 times faster inside water. You may remember inside the swimming pool, if you hit the wall and that sound transmission is faster. And likewise, it depends on the structure of the tissue. And if it's bone, much stiffer biological material, the sound wave moves even faster, okay? So the time related to the distance. So think about this as a, like, let's say round trip from here to here. So we send a sound and it goes hit and it back. So the distance is D, and the time between this travel, round trip travel was T. Then we can know length, the speed is the total distance traveled divided by time. Or we are interested in the location D, so the D can be described as the speed times time divided by 2. So this C is actually pulse travel speed, the speed of sound, and D is the distance from the transducer to the structure and to round trip. So now let's have a simple calculation. So what's the time required to receive an echo from aorta, assuming the transducer is abutted to the abdominal wall and the aorta is 6 centimeters deep. Let's say we have a transducer, we put this here, and I'm sending the sound to about 6 centimeters below aorta. Then what will be the time? So based on these formula, we can see time will be 2 times distance divided by speed. So abdominal belly, the speed of the sound will be 1.54 kilometer per second. And the distance of D is, let's say, 6 centimeters. Then if you calculate it, you get about 80 microseconds. So in electronics, usually we can detect like nanosecond order. And this tens of microsecond is nothing. It's so easy to detect this microsecond. So that's why we can do a very fast processing and real-time update of our ultrasonic images. Okay, so however, we are discussing only one direction, one line of signals. So forming an ultrasound image with transducer pointed in one direction. And then, so that will give us only one line of tissue structure, but if we can have multiple ways, we can have a 2D structure, or we can kind of rotate this directions, we can have this fan shape of the cross section. So pointing many different directions with the transducer by rotating with a motor back and forth like this. We send the sound wave like this, and sweeping motion resulting in pi wedge shape, okay, built from each line of reflection.